Hello, everyone. My name is Gunjan, and I am a staff software engineer with Google Cloud. Today, I will be talking about semantic search with vector databases. Specifically, what does an end-to-end life cycle of a vector database and semantic search look like? And before I start, a note on the motivation for this talk. So, vector databases and vector search is a fairly new capability that has only come up in the last couple of years. And in my personal journey, when I got started, this was pretty exciting. The kind of search capabilities you got and the results was a tremendous capability. But the process for learning how to do it and do it right, it involved a lot of friction and a lot of learning and relearning things which I thought I know about databases and how indexes work. So the primary motivation of this talk is to lay out the end-to-end life cycle of what does it feel like to get into a prototyping stage with semantic search. Why we may want to prefer using our traditional relational OLTP databases over dedicated databases where available, and what are some of the aspects when we talk about productionizing semantic search. And here's a quick kind of an outline of the things we'll be talking about. I will start with the quick recap of semantic search. What does it mean? And I will probably not be spending a lot of time explicitly comparing with how traditional search or, for example, B-tree indexes work or full text search work. But part of the intention as I cover this is to understand what are the common learnings that we can apply semantic search and where all we need to be extra vigilant. And yeah, after that quick overview of semantic search, then we will jump into the life cycle, starting with what are the individual steps in this end-to-end journey of prototyping and then productionizing semantic search on your database. So moving ahead, quick recap of semantic search. What does that mean? And specifically vector search to implement semantic search. A vector is a mathematical object. It has a magnitude and a direction. And embedding is the process of converting a piece of information, it could be text or it could be image or video, into a mathematical form represented as a vector. So that's an embedding. And all the LLMs that you may have heard about, OpenAI, Gemini, they provide n number of different models that can, embedding models that you can use to take your information and convert it into a vector. Vector similarity is just a measure of how similar two vectors are. There are multiple similarities, cosine, Lagrangian. Uh, Again, you can read up on that separately, but for the purpose of this talk, given two vectors, you can figure out how similar they are. And vector search is basically search powered by similarities between these vectors. Um, just a quick visual representation of what this means. You have some data set, and then you use an embedding model, deep learning model, to convert it into vectors. And once you have your vectors, you can either do a brute force comparative search between them using vector similarity. But for usual production scenarios or real world scenarios, you will need to create a vector index or a serving index. And there are dedicated vector databases out there, but increasingly you will see the most popular OLTP traditional databases, Postgre, MySQL, SQL Server, they providing this capability out of the box. And yeah, another example of how what semantic search means. For example, if I'm searching for Google Cloud or AWS Cloud, my traditional full text search will probably also return me results about Nimbus Cloud, which is a type of cloud up there in the sky. But with vector search, they will be very spaced out in that vector n dimensional space, and therefore you are expected to get results based on the semantic meaning of your data and not just the text or keywords that you have provided. Now, so this is vector databases, and why use your OLTP databases for vector search? Because again, you have all your database master data in your OLTP databases typically, and if that provides you vector search capabilities, it really simplifies the setting up, prototyping, productionizing, and the long-term maintenance overheads. Again, a different kind of view about how this works. So given your data set, initially in step one, you will generate vector embeddings for all that data. It is a fairly expensive and time-taking step, and later on, we will quickly cover some techniques of speeding that up. But once you have your data and let's say you've created your vector index, when you get a search query, you generate an embedding from your search query, and then on that embedding, you do a vector similarity search based on your vector index. And either you can directly consume those results to surface it to your application or user, or you can use that in different patterns, for example, the RAG pattern, to ground your LLM prompts better. And some more examples of where vector databases can be used are one is semantic search, what I mentioned, RAG or retrieval augmented generation, where use you can use vector search to find similar things in your data set and use that as part of your prompt to ground your prompt and get more meaningful or accurate results. Recommendation systems, now there are multilingual models where you are not just limited to data set in one particular language. Similarly, there are multimodal models where I can use the same model to generate vectors for text, image, video, and then do combined search over all of these. So pretty powerful capabilities. And again, why use your OLTP database itself as a vector database when there are dedicated vector DBs out there? Uh, it really simplifies your life. If I have a way in which I can simply run my vector queries on the OLTP database, I get high consistency. My data is never stale. There is no duplication. It has cost benefits. And one I'll be using sometimes a concrete example of Postgre as a ANN vector search. We'll come to what ANN is. And different other implementations also provide similar capabilities, but I'll be using Postgre as an example because it is a fairly popular open source offering, and the pgvector extension is the most popular extension, or at least one of the most popular extensions out there. So pgvector is fairly mature and well supported, and within pgvector itself there are different types of vector indexes. There is an older ivf flat and a newer hnsw, and later on we'll quickly cover why have multiple types of indexes. But in short, HNSW is getting more and more popular, and yeah, but it is really demanding on memory. So now, bit of caution. There'll be a lot of terms ahead. The expectation is not that you will understand everything, but again, motivation is that at the end of this talk, you will understand the end-to-end life cycle of semantic search, and you'll have a mental map of what to expect at each stage. So, closing the loop on semantic search, typically when we, for example, do a b-tree based index search, it is an exact search. Either we get the result or not. It's a yes no answer. But vector indexes usually are ANN, or approximate nearest neighbor. So they give an approximate result, and that is where the concept of recall comes in. Recall is an objective measure of how good an approximation I'm okay with. For example, if my recall is 0.95 or 95%, that means that if I would have done an exhaustive brute force search on all my vectors, if they gave me 100 result, in my ANN query, it is giving me 95 out of those 100 and maybe five others which were much lesser in ranking. But it'll do that in a fraction of a time at a fraction of resource cost. And that is where concept of recall versus QPS comes in, that when building your index or running your queries, usually you have a trade-off, and there are other trade-offs also we'll talk about, but typically you have to decide how much cost you're willing to incur for a higher recall. And this is again a product question, not always an engineering question, but that makes it really interesting while playing with vector indexes. And also there could be other constraints with vector indexes. For example, in the PG vector implementation, you can only get at most up to 1000 top end results, not more than that. And there are the actual limit may be even lesser based on the query shape. Okay. Now that we have done a quick recap of semantic search, vectors, and why Postgre as a or your OLTP database as a vector database, let's take a breath and get into the actual end-to-end life cycle of a vector search index. So many of these steps are common for any indexes that you would think about in production scenarios. Starts with instance sizing, generating and building your index, and then making sure that the index is being used in production. But there are some steps which are different, and even in these steps which we are used to, there are other concerns that we need to keep in mind. Now let's jump into it. uh, yeah, this is me when I thought I'll do a quick prototype in a matter of few hours or days, but ended up taking weeks because of so many things I was not aware of in vector indexes. Very first is sizing your instance. Sizing means that how much disk, how much memory, how much CPU do I need for serving this index. And vector databases typically are very demanding on memory. So depending on your implementation, and we'll here take HNSW as the example, we need to figure out how much memory we need to account for in our instance. For example, even before we go to the index, given a particular vector and embedding model you're using, you can use that. For example, Vertex AI has 768 dimensions, or OpenAI models have 1536 dimensions, and each dimension in an array will take 8 bytes. So using that, you can figure out what is the size of my vectors that will be stored. And then based on the implementation, for example, for HNSW, here is a very handy formula, and feel free to take a screenshot or use this deck as a reference later on. Based on the implementation, we can infer how much memory this will take when it is running. So based on that, you can do your instance sizing. And yeah, second step is generating embeddings. Like I mentioned, if you have a big data set, think in terms of millions or hundreds of millions of data points which you need to generate embeddings. It can be a fairly involved process, and you need to take care of consistency and so many other things. There are multiple solutions out there. There are managed solutions. For example, Cloud SQL has a Google ML integration, which provides you functions which behind the scenes can generate embeddings. Similarly, PostgreSQL has third-party solutions like PGA, which you can self-host and run, and or you can use many of the available application side code to do this. And LLMs usually also provide batching APIs to do this more efficiently, but you'll have to start with this one big step of generating embeddings. Once you've done the embeddings, this is one of the trickiest parts of dealing with vector indexes, which I mentioned, because in B-tree indexes, either I need an index or not. Either index returns a value or not. But in vector indexes, there is a concept of recall, and there is this quality. And depending on the implementation, for example, taking the example of HNSW, HNSW has parameters like M. HNSW is a graph based index, which means that every node has a neighborhood of nearest neighbor graphs, and that is the size M. Like how many neighbors do I want to maintain in my graph? As you increase M, you usually take more time to build the index. It'll take more space in the memory, but it usually gives you better recall. And there are n number of variables with the exponentially, combinatorial explosion of combinations that you need to try out. When you need to figure out that given my available resource and time, what is the best combination of these parameters that I should use. We'll take a look at some techniques that you can use to do this more efficiently. But yeah, this is a very important step whenever you're building a vector index. Again, there are solutions out there, vector databases, which abstract out some of these things. But in general, for example, with Postgre or some other databases, we typically encounter some of these trade-offs that you will have to be aware of. And choosing the right index type, I mentioned HNSW and IVF flat. IVF flat is older. It is usually much faster in building, but HNSW is much more resource intensive, but gives much better graph, and which is also resilient as your data changes. And yeah, Like I mentioned, these are just three of the parameters that are HNSW implementation specific. If you go with some other implementation, there'll be some other parameters. But when deciding what is the ideal graph for you, you will need to find the optimal combination of these. So you just need to do some perf benchmarking, figure out the most optimal combination that gives you the desired recall QPS. Easy, right? Yeah, yeah, again, that is part of my learning. That is a hard problem. It's more like a hyperparameter optimization problem where you have n number of variables and you need to figure out some magical combination that gives you the best value. This is one possible algorithm you can use. Again, this is valid for HNSW and even for other kind of implementations where you have n number of parameters that you need to uh, do your perf benchmarking on before you can see for each combination what is the QPS you're getting, what is the recall you're getting in your perf benchmarking. So a grid search method means that instead of doing a brute force search over all of the space, you just move in one direction and just try out the neighboring values and then eliminate the direction where you are getting the worst value. So you just kind of trace a snake like pattern across the grid, and this greatly reduces the time you take for finding the optimal parameters. Again, you will have these slides. You can use this as a reference if you really want to get deeper into how do you tune your index parameters. And this is just the same example I gave. This is QPS versus recall curve, a recall graph for each of the combinations of a perf test that we ran. So each line uh, basically tells you for a given set of parameters, as you increase your recall, how does your QPS perform? And typically, we want the best performing graph here, like you see. But again, the best performing graph may take a lot of time to build. At times, for example, twice the amount of time as compared to a graph which is slightly worse, not much worse. So again, when you do your benchmarking after grid search, then you can do a quick visual inspection to see what are the other factors that you want to optimize for. Like, do you want to spend hours or days or weeks building the ideal index, or do you have a faster index which is almost as good but much cheaper to iterate on and improve over time? And yeah, again, when thinking about vector indexes, be aware of the resources that you have and make sure that all your database, this is especially important for non-specialized vector databases like Postgre and others, where you're using the old DB database itself as a vector DB. So make sure that you are using all the available capacity, which means that make sure that your parallelism is set to use all the available cores and you are using as much memory as possible, especially during index build time. Because as soon as your memory cannot fit the graph which is being constructed, you start seeing it being paged, moved to disk, which exponentially reduces the speed of indexing. And yeah, once you build the index, verify, double check in your production, maybe using a slice of production like queries. And yeah, once you have your production database and a vector index in production, uh, there is one thing you need to be aware of, which is different from B-tree indexes. In B-tree indexes, if an index exists, it will be used. If an index is not being used, maybe because your query shapes have changed or your database statistics have changed, then it will not be used. But in ANN indexes, approximate nearest neighbor indexes like HNSW provided by pgvector in Postgre, uh, there is this concept of data drift. As you're doing mutations in your data, as you're inserting new vectors, as you're modifying older vectors, your graph changes. And depending on what kind of vector index you are using, that may lead to a change in the performance or quality of your queries. For example, IVF flat index type, it does not do very well with data drift because it does some clustering only once at the beginning, and once those center of clusters are found, they never change. And over time, as you're inserting your actual data after the initial kind of clustering, it may give you very skewed distribution of vectors. But HNSW is much more resilient. But the point being that over time, as your data drifts in production, you should be checking the actual recall you're getting over time, and if it is drifting from the desired recall or QPS. And if yes, then it may be a time to re-index. So that was a pretty fast whirlwind kind of a recap of the end-to-end life cycle, right from uh, how do you choose the right model or generate embeddings to uh, building a well-tuned index in production and maintaining it. Now, there are a bunch of techniques that are useful for scaling, and scaling becomes a big challenge in vector databases because, like I mentioned, the HNSW graph-based algorithm and many good algorithms out there are graph-based. They, by nature of them being graph-based, they require to stay in memory. Now, there are other uh, algorithms that are out there. For example, Microsoft has a proprietary disk-in implementation, which does better with spilling over to disk. Nevertheless, you'll get the best kind of performance when your index is in memory. And this and some other factors mean that you need to really think about how do you scale your data. Uh, because when we talk about vector databases, we've seen in real life up to millions or tens of millions, even hundreds of millions uh, vectors can be easily hosted on a OLTP databases, but hundreds of millions is a stretch, and billions is hard to do. So the very first technique is dimensionality reduction, which essentially means that if you have a vector of 4,000 dimensions, you should ask, do I really have that much of information content in my vectors that I need 4,000 dimensions? Can I reduce it to 768 or even 100 dimensions? And there are different mathematical techniques out there that will allow you to take this higher dimensional space and flatten it to a lower dimensional space. For example, I can use a 3D cube and flatten it to a 2D cube. That will, and when I compare the distance between these vectors, I'll get an approximate answer. There'll be an error introduced, but the amount of memory you will need to store these two-dimensional vectors is much smaller. So just extrapolate it to n-dimensional vectors, and that is the technique of dimensionality reduction. This has nothing to do with vector indexes per se. This is the technique you can employ even before you kind of ingest your embedding. So you can generate our embeddings and apply these techniques like SVD or PCA to come up with lower dimensionality vectors and do some perf benchmarking on are you getting good enough recall. So that will greatly reduce the size of vectors that on disk and in memory. Second technique is quantization. Quantization, roughly speaking, again, is like an approximation technique. There are different kinds of quantization. Some of them are pretty advanced, like product quantization. But simple quantization technique is that instead of using 8-bit floating point values, if I use only 4-bit floating point values, I've immediately reduced the size of my data to half. And similar kind of, not exactly half, but a significant reduction in the size that my index will take in memory, which directly means that I can support much more number of vectors with the same amount of resources. And again, another analogy is compressing wave into MP3. The trade-off here is that you lose a bit of accuracy, but the benefit you get is that it uses less resources. You can support more number of vectors with the same resources, and the queries itself can become faster. So yeah, there are a lot of quantizations out there. A lot of research is happening as we speak right now. So over the coming semesters and years, I expect that the most popular index types will start supporting more and more of these quantization techniques. For example, it is only in the last 6 months or so that pgvector started supporting half vec and bit kind of quantization techniques, and other uh, indexes. For example, AlloyDB has a scan index which supports SQ8 and much more advanced kind of quantization techniques. And similar other proprietary providers would be providing such advanced quantization techniques. Here's a quick kind of example. You need not understand the exact Postgres syntax here, but just to compare before and after, in practice, how it is easy to use quantization. Here, by default, if I'm creating an index using HNSW, the first example is how you will write your DTL. But if I want to use halfway quantization, I just replace I just cast my vectors to half vectors, which means instead of 8-bit, they'll start using only 4 bits in disk and memory. And accordingly, I'll use the corresponding comparison similarity operator. And I will also have to modify my queries. Instead of directly comparing my vectors with a vector on the search query, I will have to cast the search query embedding into Halfway and then compare it. But with these simple changes, I increase my capacity, not to twice, but close enough. I greatly increase. And some of the perf benefits you will see here, depending on some parameters, we've seen 2.5 to 3 times speed up with some of the benchmarks, and again, similar kind of benefit in the index size usage, which means scale. So these are very low hanging fruits, good wins that you can make use of. Then there are filtering techniques for scaling. The very first is don't use vector index. You can use pre-filtering to create indexes based on some other columns on standard SQL predicates, which and if your cardinality is low on those dimensions, by using a standard index, you may not even need to use a vector index, and you will get exact answers. So that will be a simple life. You are not worried about recall percentage, and if your recall is drifting over time. And second is partial indexes. Instead of creating a single index, for example, Postgres supports partial index where I can provide a constraint. And if I have 10 categories, I can create 4 index on the largest categories and the fifth index on everything else. Then there's a partitioned ANN indexes. Again, this is more implementation specific. This technique is right now Postgres specific, but a similar technique definitely exists in Oracle and any other OLTP databases of your choice. So the technique is that use your database specific features to create partitioned indexes, which the database, for example, takes care of managing behind the scenes. And then there are iterative index scan. This is a very Postgre pgvector specific technique that if you do not get enough results in the first go, then you keep scanning so that you don't lose out on the recall. And yeah, that takes us to the end of this presentation. And it was a lot of content. Again, just to recap, the motivation was that by charting out the end-to-end life cycle of a vector index, including steps that are similar to how we usually do our scaling and sizing and productionizing of regular indexes, but highlighting what different factors we need to keep in mind, and also laying out what different additional steps you need to be aware of when working with vector indexes. This will build a quick kind of a mental map of the end-to-end journey. At a prototyping stage, you can skip many of these, but when you need to come to production, having this mental map really helps. So yep, wishing you all the best, and happy to connect if you are interested in talking about any of these techniques, or if you are trying some of these out, and or if you have feedback on any of the work that we have presented, please reach out. And yep, thank you so much.